Very good afternoon, everyone, once again, and welcome back to the live tutorial session. So, any doubts on the lab 4? Any questions on lab 4? So, lab 4 based on photoelectric effect. So, you need to do two parts. One is to find the work function for different materials, that is metal, and another one, choose any one metal out of three. The options are given on that. So any one metal you choose it and change the wavelength and the corresponding stopping potential you need to find out. Okay. And then you need to plot a graph. From the graph, you need to find the parameters, work function, threshold frequency, and the Planck's constant. Okay. So try to do that and complete the report by next Tuesday. Okay. Now we can start our session tutorial for the last part. Slide 2. Okay. So let me share the screen. Yes. So like 2. So in like 2 we seen two topic. One is diffraction. One is diffraction and another one is photoelectric effect. So diffraction, the pattern is entirely different from interference pattern. So the pattern we call it as central maxima. So central maxima means 2x. What is x? X is given by lambda L over D. Okay, so this is the width of the slit, capital D. And the condition also changed. For dark band, the condition is D sine theta equal to M lambda. And for the bright, this one for bright fringes, and this one for the bright, D sine theta equal to M plus 1 over 2 lambda. So both here the M value is 1, 2, 3. There is no 0. So both we have M equal to 1, 2, 3, 4, etc. Okay. And then if the slit is narrow, narrow means like this, whether horizontal or vertical slit like this. Narrow slit means we have formula D sine theta equal to sine theta equal to lambda over D, or D sine theta equal to lambda. Or if the slit is in the shape of a circular one, the shape of the slit is circular, then we can use this formula, sine theta equal to, that is path difference is equal to 1.22 times lambda. Okay, lambda over D, we call it as the circular shape of the slit, if the slit is in circular shape. Okay. Then photoelectric effect. So photoelectric effect, we already know that light falls on a material. What happens? Electrons are emitted. Okay, whether all light will emit electron? No. Light of only certain wavelength or light of only certain frequency will emit wavelength. That frequency is called threshold frequency, and that metal possesses energy called work function. That is work function HF naught. This is called work function. And this is the energy of each photon, photon energy. Okay, so this energy is used in two ways. One is to remove the electron called work function, and another energy, part of the energy is used to move the electron called kinetic energy. Okay, so the incident energy is used in two ways. One is to remove the electron, that is called work function, and another one is to move the electron, we call it as kinetic energy. Okay, so the kinetic energy, we already know the formula, half mv square, and to measure the kinetic energy, we need to supply a voltage which is called retarding potential or stopping potential to measure the kinetic energy. So this is the stopping potential, E times V naught, that is equal to kinetic energy. Okay, this is called the stopping potential. So these are the formulas we are going to use for today's tutorial session. Okay, today's tutorial session we are going to use this one. Okay, any questions? Okay, now move on to the first problem. Okay, diffraction. So whenever the problem is given, you need to identify whether the problem is belongs to diffraction problem or interference problem. So it is easily identified by using the single slit. So when the problem says light passing through a single slit means the problem is belongs to diffraction. When there is a pair of slit or slit separation, we call it as a pair, then the problem is interference problem. The problem belongs to interference. Clear? Okay. Now, look at the problem. A light passing through a single slit, that means diffraction problem. A light passing through a single slit, and the width of the slit is, that is D value. We call it as D. So 0.056 millimeter, and form a diffraction pattern. Form a diffraction pattern on a screen which is 2.6 meter away, that is L value. The central maxima is 5.9 centimeter wide. That means this is the central maxima, the pattern. Okay, so this is the central maxima. So we call this is the center line. Okay, so this is the center line. We have the single slit here. So we get the pattern, the center maxima. So this is called a central maxima. So this distance is called 2 times x. Okay, and then we get the dark image. So this is dark. We get the dark image. And then we get the bright image. So the size will be reduced. So this is the bright image. Like that, the pattern goes on. So what the problem says that the central maxima, that means 2 times x is equal to 5.9 centimeter converted into meter is given. 5.9 into 10 power minus 2 meter is there. So what we need to find out, find the wavelength of the laser light. Find the wavelength of the laser light. So what is the formula for x? The formula is lambda L over D. For x, lambda L over D. So instead of x, I can substitute the formula. So what is the formula? Lambda L over D equal to 5.9 into 10 power minus 2 meter. So our aim is to find lambda, keep lambda and move everything on the other side. So 5.9 into 10 power minus 2 into D. What is D? 0.056 10 power minus 3 millimeter. Millimeter means 10 power minus 3 divided by L value. So 2 times L, 2.60. So when I do that in the calculator, what happens? I will get the answer as 5.9 10 power minus 2 into 0.056 10 power minus 3 2 into 2.60. So I am getting 635.4 nanometer, that is 10 power 9. So I am getting like this 635.4 nanometer. Nano means 10 power minus 9. Okay, nanometer I am getting. Okay, so I am getting this value. Clear? Okay. Any questions? Okay. Next question. Look at the next question. The problem says that light of wavelength 750 nanometer passes through a slit 1 into 10 power minus 3 millimeter. That means D is equal to 1 into 10 power minus 3 into 10 power minus 3. So totally how much? 10 power 6. Okay, so 10 power minus 3, another one more millimeter is there. So 10 power minus 3 minus 3. So we get totally 10 power minus 6 meter. And how wide is the central maxima? How wide is the central maxima? We need to find out. How wide is the central maxima? So milli means 10 power minus 3. Minus 3, not plus, minus. It is not plus, minus 3. Milli. Okay, 10 power minus 3, it is not plus, minus. Okay, if it is plus 3, you can write 1 kilometer, no problem. Okay, now, how wide is the central maxima? That means central maxima, look at the diagram, central maxima up to here. So we need to find the distance. So we know the formula for x. X is equal to, what is the formula for x? X is equal to lambda L over D. We know that. So what is the lambda? 750. 750 nanometer, 10 power minus 9. L is 20 centimeters, so 0.2. Divided by D. What is D? 1 into 10 power minus 6. So what is that value? X value. I can put it in the calculator. 750 nanometer, 10 power minus 9. Nanometer, 10 power 9. So 0.2 into 1.2 0 into 10 power minus 6. So we are getting the value is 0.5 meter. That is x value. But central maxima means central maxima. So central maxima means 2 times x. Okay, 2x. So that means 2 into 0.15. So that is equal to 0.3 meter. So that is the answer. So 0.3 is the answer. Okay, 0.3 is the answer. Clear? Got it? Okay. Now take the tutorial question number 2. Number 2 in the tutorial question. What the problem says, light of wavelength 441 nanometer incident on a narrow slit on a screen 2 meter away. The distance between the second diffraction minima, that means m equal to 2, and the central maxima, that is from the central maxima, that is 1.5. Calculate the angle of diffraction for the second maxima or second minima. So we know the formula. What is the formula for minima? For minima, what is the condition for minima? For minima, the condition is d sine theta equal to m lambda. D sine theta equal to m lambda. So here what is d? We don't know d also. We don't know the theta also. So we cannot use this formula. Maybe we can use that formula, tan theta formula. What is tan theta? Tan theta equal to y divided by L. So here y is given because the problem is given as from the, sorry. So the problem says that from the central maxima, okay, so the problem says that from the central maxima up to the second bright, okay, second dark, second minima means dark. So this is central maxima up to here. So x means from here to here, okay, this value. And then we get the first bright. This is first bright, and then the dark, first dark. This is first dark. Okay, this is dark and this is bright, and then we get the dark image. So this is dark. This is m equal to 1 and this is m equal to 2. Second means m equal to 2. So what should be this angle? So this is the slit, and from the slit to here. So what should be this angle? We need to find out. So this distance is given in the problem. How much? 1.5. So this is y value and this is L value. So tan theta. So from that we need to find the angle. So what is that angle? Theta is equal to tan inverse of y by L. So that is equal to tan inverse of, what is y? Y is 1.5 centimeter. So 1.5 10 power minus 2 divided by L. L is 2 meter. So what is that angle? So tan theta divided by 2. So I am getting 0.43 degree. I am getting this angle. 0.43 angle. Okay, now, so this is part A. So part B, we need to find the D value. So we can put that one. D is equal to, this is B. So D is equal to m lambda by sine theta. So what is m? M equal to 2 because second bright. M equal to 2, lambda is equal to 441, 10 power minus 9 divided by sine 43. Sorry, 0.3, 0.430. 0.430. Now what is the answer? 2 into 441, 10 power minus 9 divided by sine 0.43. So I am getting 117.5 micrometer. So the answer is 117.5 micrometer I am getting. Okay. So first I tried with this formula, but I cannot able to do that because D is missing, angle is missing. So we cannot able to do that. So first to find this one angle and then go with the D formula to get the answer. Okay. Any questions? Any questions? Okay. Any questions you have? Okay. Move on to the next question. Look at that. All the questions are very similar. We are going to use the same formula again and again to solve that. Look at the problem. A beam of monochromatic green light is diffracted by a single slit of width 0.55 millimeter. The diffraction pattern formed on a wall 2.06 meter beyond the slit, that is L value. The distance between the position of zero intensity on both sides of the central bright fringes is this much. What do you mean by zero intensity? So I shown in the lecture material the intensity pattern. So this is the intensity pattern like this. So here the intensity is 0. After that, the small bump, bright image, and then the intensity will be dropped like this. So here also the intensity will be small peak and then the dark image and then the peak and then vanishes like that. So zero intensity on both sides, where this is a zero intensity, this is the zero intensity on both sides. So from here to here, the distance is how much? 4.1 millimeter. So 4.1 millimeter. Okay, calculate the wavelength of light. That means what is this value? This is called 2x. So 2x is equal to 4.10 into 10 power minus 3 meter. So what is that x value? We know the x value is lambda, okay, lambda L over D equal to that one, 4.10 10 power minus 3. Now we need to find the wavelength. So from that, what is lambda? Lambda is equal to, so 4 times 10 power minus 3 multiplied by D. D is 0.550 millimeter divided by 2 times L. What is L? 2.06. So what is that answer? What is that answer? So 4.10 10 power minus 3 multiplied by 0.550 10 power minus 3 divided by 2 times 2.06. We are getting the answer as 547.3 10 power minus 9 meter, or approximately 547 nanometer. 547 nanometer. So we get the same thing. Okay, we get the same thing. Okay, next problem. So the next problem is also the same thing. A slit of width W1. There are two slits. Okay, the first slit is 2.6 into 10 power minus 6 meter. When light of wavelength lambda 1, 510 nanometer passes through the slit, the width of the central bright falls on the flat observation screen has certain values. We don't know what is that will be. Okay, and for wavelength lambda is equal to 7 with the same screen kept at the same distance, the width of the slit is W2. Okay, so W1 is replaced by W2. The screen distance is same, but the wavelength is different. So the wavelength is 740 nanometer is used. Now what happened? The width of the central bright fringes on the screen is observed to be unchanged. How come it is unchanged? Because the formula says that lambda x is equal to, that is the pattern, lambda L over D. If lambda changes, because increasing, see from 510 to 740, if lambda increases, this value increases. But the problem says that this is unchanged. That means this value decreases. To unbalance this unchanged one, so the width of the slit will be balances. So we need to find what should be the width of the second slit. So if lambda increases, means definitely this will increases. But the problem says that the width of the central bright fringes are unchanged. That means remain same, no change. Okay, they are same. They are same. That means this value decreases to compensate the increase in fringe. Okay, so that means what is given? The x1 is equal to x2. So what is the formula? Lambda 1, same distance L, W1 is the width of the first slit, equal to lambda 2 L divided by W2. So L get cancelled. So what is W2? So W2 equal to lambda 2 divided by lambda 1 into W1. So what is that one? Lambda 2, 740 nanometer divided by 510 nanometer. So nanometer get cancelled into W1. What is W1? 2.3 into 10 power minus 6 meter. So what is that value when I divide it? When I divide it, 740 nanometer. So nanometer can cancel. So 740 divided by 510 into 2.3 10 power minus 6. So look at that. The width will be 3.34 into 10 power minus 6 meter. 3.34 into 10 power minus 6 meter. Okay. Any questions? Any questions here? Okay. Let's move on to the next problem. Tutorial question number 11. Light of wavelength 580 nanometer falls on a slit that is 3.8 into 10 power minus 3 millimeter. Always remember, because in the examination many students forget to put this millimeter. They will consider only this, but they forget this one. So the answer becomes wrong. So be careful about that. Okay. So that means what is the value? 3.8 into 10 power minus 6 meter. So totally we get micrometer. Okay. Now estimate how far the first bright means m equal to 1. Diffraction fringes is from the central strong maxima if the screen is 10 meter away. So how far the first bright? We need to find out. So we need to find the y value. Okay, so this is the pattern. We know the pattern here. So this is the central maxima. The entire thing is central maxima. And then we get the dark. So this is the first dark. And then we get the bright. So this is the first bright. Okay, so this is the bright. So they are asking to measure this distance. How far is the first bright? So we need to find this value. So this is the first bright. We need to find out. So this is the slit. Okay, we get the slit. So what is this distance? 10 meter. L is equal to 10 meter. Okay, so we need to find the value of the distance d. Okay, so how to do that? So for maxima, what is the condition for maxima? So the condition for maxima is d sine theta equal to m plus 1 over 2 lambda. So what is m? M equal to 1. So we need to find the angle. Okay. So sine theta is equal to 1 plus 1 over 2 lambda. What is lambda? 580 nanometer divided by 3.8 into 10 power minus 6. And then what is angle theta? So when you do that, so 3 into lambda 5.8 10 power minus 9 divided by 2 into 3.8 10 power minus 6. So take the sine inverse. We get the angle is 13.2 degree. Then what is the formula to calculate y? Y is equal to tan theta times L value. So what is tan theta? That is tan 13.2 degree times 10. L is 10. So tan multiply by 10. So 2.35 meter. 2.35 meter. That is the distance. So 2.35 is the distance. Okay, clear? Any questions? Any questions here? So all the problems pretty straightforward only. Huh? Okay. Look at this problem. Coherent light from a laser diode is emitted through a rectangular slit. So the slit is in the form of a rectangle. So 3 micrometer versus 1.5 micrometer. So this is the rectangular slit, and 3.5, that is rectangular, means the slit should be like this. Should be like this. So 3 micrometer into 1.5 micrometer. 3 micrometer into 1.5 micrometer. So 3 micrometer is horizontal and 1.5 is vertical. That's it says horizontal by vertical. So this is 3 micrometer and this is 1.5 micrometer. Clear? Okay. Now determine the laser wavelength is 780 nanometer. Okay. Determine the angle between the first diffraction maxima. First diffraction maxima for above and below the central maxima. And determine the angle between the left and right side of the, again the first one, first diffraction maxima for above and below, left and right. What do you mean by above and below? What do you mean by above and below, and what do you mean by left and right? Okay, so in order to explain this, I go back to the lecture slide. I can go back to the lecture slide to explain that phenomena. What do you mean by above and below and left and right? Okay, let me share the screen. Okay. So now you can see the lecture slide. Now, yes. Now see the shape of the slit. Now the slit is in horizontal position. Look at the slit on the second diagram. The second diagram, the slit position is horizontal. Look at that horizontal. Suppose if it is vertical like this, what happens? If it is horizontal, look at the pattern. This is a central bright. The pattern is above and below. So this is above and this is below. If the slit is horizontal. Suppose if the slit is vertical, what happens? If the slit is vertical, what happens? I will get left and right. So I will get the pattern should be like this. Okay, left and right, I will get it. So now for horizontal, I am getting above and below. Above, dark and bright, below, dark and bright. Suppose if I use vertical, I will get left side and right side. Left side and right side. Clear? Okay. Are you able to understand the diagram? So why the problem says left and right side? Because of the position of the slit. Whether the slit is arranged horizontal or the slit is arranged vertical. Okay. Based on that, I get the pattern. Okay. So go back to the tutorial question. So go back to the tutorial question. Now you can see that if I use that in horizontal position, what should be the value of central diffraction minima? Okay. So now for horizontal, what is the width of the slit? For horizontal, the width of the slit D horizontal is equal to 3 micrometer. 3 micrometer. So we need to find the angle only. Angle is important. So what is the condition for minima? D horizontal sine theta equal to m lambda. So first minima means 1. So what is the angle? Theta is equal to sine inverse of 1 multiplied by lambda, 780 nanometer divided by dh, that is 3 into 10 power minus 6. So what is that angle? So angle equal to 1 into 780 10 power minus 9 divided by 3 into 10 power minus 6. Okay. So 780 10 power minus 9 divided by 3.3 into 10 power minus 6. Okay. So I am getting the angle is 15.07 degree. So this is angle is from above only or below only. So above and below means multiply by 2. So above and below means this angle is only above. So above and below means multiply by 2. So above and below means angle is equal to 2 times. Okay, 2 times. That means 30.4. Okay, 30.4. Okay, we get the answer. Similarly, we can use the vertical slit. Similarly, we can use the vertical one. So what is the vertical slit? vertical slit dV is equal to 1.5. Yes, oh sorry, 30.14. Okay, so 30.14. Okay, 30.14. Okay, so micrometer. So again, use the same formula. Instead of dH, we use dV. Sine theta equal to m lambda. So sine inverse of, sorry, theta equal to sine inverse of, so 1 into 780 10 power minus 9 divided by dV. dV is 1.5 10 power minus 6. So what is that angle? And then what is 2 theta? Okay. So sine inverse of 780 10 power minus 9 divided by 1.5 10 power 6. So we will get the answer as 31.3. So the angle is 31.3 multiplied by 2, so 62.6 degree. So we will get the answer as this much. Okay, 62.6 degree. Okay, pretty straightforward. So that's all about the diffractions. Now comes to the photoelectric effect. Now, for a sodium, the work function is 2.3 electron volt. Does sodium exhibit photoelectric effect for yellow light of wavelength 580? We need to check it. So for photoelectric effect to take place, what we need is the incident energy is equal to HF should be greater than the work function of the metal. So if the energy of the photon is greater than the work function of the metal, then only photoelectric effect takes place. So work function is given. We need to check the energy. So what is that energy? Energy, okay, energy is equal to HF, that is equal to Hc by lambda. So what is H? 6.63 into 10 power minus 34 joules second. Speed is 10 power 3 into 10 power 8 meter per second divided by lambda. What is lambda? 580 meter. So seconds, meter. What is that answer? Meter get cancelled. So the answer is in joules. 6.63 10 power minus 34 multiplied by 3 10 power 8 divided by 580 10 power minus 9. So what I am getting is 3.4243 10 power minus 19 joule. But this one given in electron volt. So we need to convert the energy into electron volt. So what is that energy in electron volt? So 3.43 into 10 power minus 19 into 1 electron volt divided by 1.6 into 10 power minus 19 joule. So this is joules. So joules get cancelled. Then what is the answer? So the given energy is 6.14 electrons. So 2.14 electron volt. That means less than. So energy is less than the work function. So no photoelectric effect takes place. Okay, no photoelectric effect takes place. Clear? So we can prove that this incident photon does not produce photoelectric effect because the energy is less than the work function of the sodium. Energy is less than the work function of the sodium. So we won't get any photoelectric effect. We won't get any photoelectric effect. Right? Okay. Next problem. UV light of radiation of wavelength 250 nanometer is incident on a clean zinc surface. Given that the work function of the zinc is this much, 3.07. What is the kinetic energy for the fast moving electron? Kinetic energy of the fast moving electron. So what is the kinetic energy formula from the instant equations? Kinetic energy is equal to HF minus work function. HF minus work function. Okay. So work function is there, incident photon is there, we can find the kinetic energy. So fast moving means with the maximum energy. So we can substitute that one. So EK, so this one is nothing but HC by lambda. HC by lambda. We can come because lambda only given. So lambda only given, so we can put that one. So what is H? 6.63 10 power. This is very important. Okay. The reason is this is in different unit. Joule second. This is electron volt. So always be careful. Into 3 into 10 power 8 meter per second minus that value. So divided by lambda. What is lambda? 250 nanometer. So everything is here is meter. And this one is work function. What is work function? 3.07 electron volt. But this has to be converted into joule. So please be careful. So 1.6 into 10 power minus 19 joules divided by 1 electron. 1 electron. So electron volt get cancelled. So meter, second. Now everything is in joules. So we can do that now. So conversion is very important. 6.63 10 power minus 34 into 3 into 10 power 8 divided by 250 10 power minus 9 minus 3.07 divided by, sorry, multiply by 1.3, 1.6 into 10 power minus 90. So I am getting an energy of 3.044 into 10 power minus 19 joules as kinetic energy. So this is the kinetic energy of electron with the maximum speed. With the maximum speed. Okay. Now, what is the kinetic energy for the slowest moving electron? Slowest moving means velocity is 0. So velocity is 0 means kinetic energy is almost 0. Okay. Slow moving means not moving. That means velocity is 0. So kinetic energy is 0. Kinetic energy is 0. Okay. Now, what is the cutoff frequency for the same problem? So cutoff frequency or threshold frequency, the term all are same meaning, threshold frequency, cutoff frequency, the meaning is same. So what is that one? Work function is equal to hf naught. What is work function? This implies 3.07 electron volt into converted into joules. So 1.6 into 10 power minus 19 joules divided by electron joule. So here also electron volt. So this get cancelled, equal to H 6.63 10 power minus 34 into F naught. So what is F naught? So 3.07 multiplied by 1.6 10 power minus 19 divided by 6.63 10 power minus 34. So I am getting the threshold frequency or cutoff frequency 7.4, 1 into 10 power 14 hertz. So the unit is hertz. Okay. So 7.4 into 10 power 14 hertz. Now what is the cutoff potential? Cutoff potential is EV naught is equal to kinetic energy maximum. So what is the kinetic energy maximum? The first problem is 3.044 into 10 power minus 19 joules. But this should be in electron volt. So convert into electron volt. So multiply by 1 electron volt divided by 1.6 into 10 power minus 19. So electron volt is given by 3.044 10 power minus 19 divided by 1.6 10 power minus 19. So the answer is 1.93 electron volt. 1.93 electron volt. So using the same equation, we need to do all the problems. Okay. Any questions? So the problem number 18, 19 and 21 and then this problem. So these three problems we will do in the next tutorial sessions. That means next week. So we will do this problem in the next week. Okay. Any questions? I can stop here and we will do the rest of the problem in the next week. Any questions? Maybe we will do it in the lecture section itself so that everyone will know that. During lecture session, I will complete this problem so that everyone will know that. So next week, lecture session means, because we already finished our topic, so lecture session is over. We will do the revision for the final exam. I will example B, 0. Example B is 0 because slow moving means electron is not moving. Electron is not moving. So when it is not moving means velocity is 0 means no kinetic energy. There will be no kinetic energy. Okay. Okay. So thanks for joining the session. Take care and bye for now. We will do the rest of the problem in the next session as well as some tips for the final exam. Okay. So how to face the final exam. We will do that one. Okay. So thank you everyone and try to complete the assignment 2 as well as the lab report 4. Okay. And I will update the marks for the lab 2, 3 and 4 as soon as possible. Okay. So before the final exam, I think you may know your coursework marks before the final exam. Okay. Thank you. Thank you, everyone. Bye. Take care. Thank you.